Hey guys, hope everybody's doing all right. What we're going to do right now is take a look at something called isomers, and this will try to help us wrap up Unit 1 here. It's not too long of a lesson, but it's a good way to kind of tie some things together and wrap things up here. So sometimes you can have more than one equivalent Lewis structure that's possible for a compound. So that's what an isomer is. It's really important to understand this, though. It's different from a resonance structure, okay? So, unlike a resonance structure, isomers have the same molecular formula, but a different skeletal structure, okay? So you'll see what I mean in a minute here. They also have different properties, okay? Something with some resonance structures really that's not going to alter the properties of that compound. Isomers, though, various isomers, with the same chemical formula, they're going to have different properties based on different polarities, probably. So we'll take a look at some of those here. A good example to start out with is some isomers of C4H10. So that's butane. You probably think of butane, C4H10, you probably picture it as a straight chain alkane, right? A straight chain hydrocarbon. And that's what we have here. So your 4 carbons, it's your 4 carbon chain, your 10 hydrogens around it, okay? You could, though, draw the Lewis structure like this, where you have 3 carbons in a row, and you have a CH3 group branched off of the middle one. Okay, so the name of this gets into some organic chemistry nomenclature here, but it's 2-methylpropane. So, not that this matters right now, but a CH3 group is called a methyl group. The 2 stands for it's being branched off of the second carbon, okay? So 2, second carbon, methyl, CH3. Propane is your chain. So you have 1, 2, 3. A 3-carbon chain is propane. So there's a crash course in OChem 1 for you, the first 5 minutes of that class. So 2-methylpropane is what you have, but it's just an isomer of C4H10. So if you look at how many carbons and hydrogens you have, it's 4 and 10. So the molar mass, 58.12 grams per mole. Same thing with 2-methylpropane. The formula is the same, right? Look at how the next couple things differ. So the melting point is different, boiling point is different, and density is different. Okay? We will talk more about this. This will be really important when we get into our Unit 2 material, which is more of a focus on intermolecular forces. So we talked about this in honors a little bit. You have a straight chain alkane here, and this is a branched one. If you have another butane molecule attracted to this one, they're going to be able to be a little bit closer together. There might be some more London dispersion attraction because it's a straight chain hydrocarbon. Therefore, like with 2-methylpropane, it's harder for 2 of these to get next to each other very well. Okay, so since this is straight, another straight chain butane could come right next to it. So look, that makes sense, right? The density is a little bit higher. Density is how tightly packed something is. So if I have this and I have more of them that could be near it, they could be closer, like more closely packed, right? So the density would be a little bit higher than the 2-methylpropane. So that's kind of cool to look at. The melting point should be a little bit higher. It should take a little bit more work to melt butane, and that's true. Negative 133 is bigger than negative 159. And the boiling point should be less as well. It should be higher, I mean. So you have a negative 0.5 and a negative 11.7. So it's a little bit more difficult to boil butane than it is to boil 2-methylpropane based on the intermolecular forces, and the structure of these. So these two are relatively nonpolar, but when you have some different polarities with isomers, that's when some more changes in properties come into play. So the question on the screen says, are these isomers? The answer to that question is yes. They have the same chemical formula. This is a benzene ring. You'll learn about that in organic chemistry. You'll draw millions of those. So you have 2 chlorines. 2 of them are in an ortho position, which is right next to each other. Meta, which is one carbon apart, okay, and para, which is on the opposite end here. So if you're not sure what this really means, any sort of intersection you have here, carbons are there. Okay, so you have a carbon here, 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 here. You have 6 carbon ring. Double bond, single bond, double bond, single bond, double bond, single bond. Okay, Something you don't see here are hydrogens. So right here, where the mouse is, there's a carbon there, and that carbon has a double bond and a single bond. It's only 3 bonds, right? Carbon makes 4. There's a hydrogen branched off of here that we don't write. Okay? So you have like carbon with the hydrogen, same thing, 1 hydrogen here, here, and here. And then you have your chloride groups branching off of it. So these are isomers because the formula is the same, right? But you have a different skeletal structure. You actually have the chlorine next to each other here, a carbon in the middle, and 2 carbons in the middle. So that's important to understand. So the next question, the follow-up here, will they have the same properties? The answer to that is definitely not. Chlorine has a relatively high electronegativity, right? It's one of the top elements. I think it's like the 4th highest or something like that. So chlorine wants electrons pretty bad. And you can see over here, this one you would have, you'd have a dipole moment. You have your dipole arrow here, dipole arrow here. Okay, there's really no electron pull over here, so you're going to have a partial negative in this end of the molecule, and your partial positive over here. So this will be the most polar of the 3 structures. This one will be a little bit less polar, but you still have a dipole arrow here, dipole arrow here. So you're going to have your partial negative and your partial positive. But over here, it's a different story, right? So you have dipole arrow up, dipole arrow down. Okay, this is more, so they kind of cancel out, right? But more nonpolar character for the para structure. We're going to do a lab, hopefully, in Unit 2 with this. Okay, this is para dichloro, 2 chlorines, benzene ring, para dichlorobenzene. All right, so that takes care of that little discussion there. So I jumped ahead a little bit here. Which of the following isomers has a dipole moment of 0? That would be number 3. I just showed you that on the previous slide right here. So the dipole moment of 0 really means the dipoles kind of cancel out nonpolar. So you end up with number 3 for that one. Okay, so one of the last things on that note sheet, I think, says draw a Lewis structure for dichloroethylene H2C2Cl2. And to answer these questions about it. So I have it on the next slide, I think, or here it is. So this is dichloro, 2 chlorines, ethylene. All right, this is one valid Lewis structure. There are a few more that I'll look at in a minute there. But let's just focus on this one. I think this is the one that's on your note sheet. So how many pi bonds and how many sigma bonds does it have? So let's knock this out real quick. We'll do sigma bonds first. You have 1, 2, 3, 4, and there's a double bond here. One of the double bonds, like one of those, is a sigma. So 1, 2, 3, 4, 5. So we have 5 sigma bonds. And how many pi bonds? The other bond in the double bond will be a pi. So that's 1. So 1 pi, 5 sigma. What type of hybridization for the carbon? So here's your carbon. They're both basically the same here. You have your carbon, and there's 1, 2, 3 electron groups around it. I know it's a double bond, but remember we only count that as an electron group. So you have 3 basically domains here, right? 1, 2, 3, 3 domains. 3 domains is a trigonal planar, so it's sp2 hybridization. All right. Is it planar? Just said that, yes, because you have a trigonal planar right here off of this carbon, and this carbon is also a trigonal planar. Okay, so trigonal planar for this, right? So the molecule is planar. Yes, that would lay flat on your desk if you built it. Do any isomers exist for this structure, and if so, how many? Well, remember, an isomer is when you have a different actual structure, okay? So I could take this chlorine over here and actually move it up here, all right? So I can make this a chlorine and move that hydrogen down here. All right. This can't rotate. Double bonds cannot rotate. So it's not like I could just rotate this and have it be back to how it was. You just rotate the Cl down and like just twist it. I can't do that. So if the chlorine's actually up here and the hydrogen's down here, that's a different Lewis structure, right? So that's one of our isomers. Another thing you can do is bump this chlorine over here, move it here where this hydrogen is. So let's do that. So we could bump that chlorine over here, bump this hydrogen over here. Okay, so you can also have chlorine, the two chlorines on the same carbon and the two hydrogens on the same carbon. That's another isomer. So I have them on the next slide right here. Okay, so the one in the middle, or the one on the left, is the one we started with. Okay, then you have these two more. So let's look at the three isomers to wrap up the lesson here. Can any of the isomers be rotated? So that is a no, right? Double bonds you cannot rotate. So you could rotate this carbon-hydrogen bond, but you're not really doing anything, right? The hydrogen might just move around a little bit, but it's just still in that location, right? It's not like I could twist the molecule right here and twist that hydrogen down and that chloride up, or that chlorine up. Okay, I can't do that. So none of these could rotate. So that means the atoms are stuck where they are. It says a pure sample of one of the following was found to have a zero dipole moment. Which one is it? So let's figure it out. So we have our chlorines down here. So dipole arrow down, dipole arrow down. Both poles are going down, no pole going up to cancel. So it looks like I have a partial negative, partial positive. So there's a dipole moment there. Here I have a dipole arrow down and to the left. Here I have it up and to the right. Sorry, it's so sloppy. So think about this. I have down to the left, up to the right. That pretty much cancels out, right? So I don't think I'm going to have a dipole moment here at all. Let's just double check over here. Dipole arrow up and to the right, down and to the right. So the up and down kind of cancel, but the right has nothing to cancel. So we have a dipole moment here, partial negative, oops, partial positive over here. Okay, so dipole moment here, dipole moment here. So dipole moment on A and C. Letter B, dipole moment of 0. Okay, so you can see the answers here on that one. Okay, that's the end. So remember, this is, isomers have a different skeletal structure. I'm telling you, students make this mistake all the time. A resonance structure is something like ozone, all right? So which, I mean, you're going to see that a billion times. Ozone, you have O double bond, O, and then a single bond, O, right? Because ozone is O3. All right. Let's see. Lone pair, lone pair, lone pair, lone pair, lone pair. 1, 2, 3, 4. I think that's it. Okay, so that's ozone, right? So you have O double bond O, single bond O. That double bond, like those delocalized electrons, they really bounce over here, okay, bounce back, all right? So you have O, single bond O, double bond O. Like those are your two resonance structures, right? The skeletal structure is still the same, right? You have O double bond O and then a single bond O, all right? Well, over here, like these isomers, you actually have the chlorines in different spots, right? The oxygens are all in the same spot here. We have a double bond moving around, or the delocalized electrons moving around, I should say, but you don't actually have a different skeletal structure. It's OOO, right? Here you have the chlorines on the bottom, here they're opposite, here they're on the right versus the left, or versus the bottom. So you can see they're actually attached to different things. So that's the main difference there. It's on your test. You want to make sure you understand the difference between those two. Know what a resonance structure is, same skeletal structure, but delocalized electrons. So your resonance structures are going to involve double, maybe triple bonds, and your isomers are an actual different skeletal structure in and of itself. Okay, if you have any issues, let me know. But anyway, that wraps up the unit, and that wraps up a little mini lesson on isomers. All right, guys, thanks.